Hey there, physics folks. This video we're going to take a look at the practice problems we did in class having to do with the introduction to non-conservative forces in energy conversion problems. So the two problems were both about a roller coaster that has a near vertical section. The first part, example 10 from the book, there is no friction, okay, where it says neglect friction. In the second part, we're going to do the same. You look at the same roller coaster, but we're actually going to consider friction. Again, I made a little bit larger document so you guys could see a little bit better of what's going on. And let's go ahead and get started. So the first one says it is the King de Ka, which is a giant among roller coasters, located in Jacksonville Township, New Jersey, is a ride that includes a vertical drop of 127 meters. So that's this section here. Suppose the roller coaster has a speed of 6 meters per second at the top of the drop, and neglect friction and air resistance and find the speed at the bottom. So you can see in the picture here what it basically looks like. What I'm going to go ahead and is just draw a little bit simpler view, something like this. We have the car that's up here with wheels and car down here, and we're going to drop a distance of 127 meters. We could consider that the height, and we know that it has an initial speed v0 of 6 meters per second, and we are to find the final velocity down here. Okay, now in order to do this, we're going to consider conservation of energy. And so we know that the car starts out with certainly some potential energy because it's above a reference point, and it also has some kinetic energy because we have a speed at the beginning. At the bottom, we can call this our 0 point if you want, and we can say that it has no more potential energy and it is all converted into kinetic energy. So using this concept of total energy in the beginning equals total energy after, we can simply say the kinetic energy at the top, and actually I usually write potential energy first, so I'll go ahead and do that, plus the potential energy, kinetic energy at the top, that's up here, equals the potential energy, final, and the kinetic energy final. There should be a plus sign in there. Now right away, we already said that this is going to have almost 0%, it will have zero potential energy at the bottom, so we know we can cross out this potential energy because it is 0. And we know that because it's, of course, at a height of 0. We can expand these to show what they actually equal, which is, of course, mgh naught plus 1/2 mv naught squared equals just the kinetic energy, 1/2 mv final squared. And now we're trying to find the final velocity here. So let's go ahead and simplify. Everybody brought mass to the party. And when we simplify this, I usually multiply the whole thing by 2, and so that we end up with something that looks a little bit like this. That goes away, that goes away. And so you end up with this very familiar expression where VF equals the square root of V0 squared plus 2GH, which looks an awful lot like the solution from the fourth equation of kinematics. Let's go ahead and plug and chug, and we're going to end up with 6 meters per second squared for V0 squared plus 2 times 9.8 meters per second squared for G times 127 meters as the height above the reference point. And when we do the chugging of plug and chug, we end up with VF equals 50.251368 if you want to take it all the way, meters per second, and that checks out to 50.3 meters per second. Now, this is a very simple energy conservation problem, much like we've done before, and because we are taking no friction and no air resistance into account, we know that all the energy at the beginning ends up as all kinetic energy at the end, and so we can find the speed at the bottom. Okay, now that's the first part, and that's just a standard, straightforward conservation of energy problem. In the next video, we'll take a look at the second part, which we will consider a more real-world situation where we will consider non-conservative forces such as friction. See you next time.